the differential equation of linear momentum. This section uses an elemental volume to derive Newton's law for a moving fluid, an alternate approach, which the reader may pursue would be force balance on an elemental moving particle. Having done it, the next section, previous section for conservation, we can move along a little faster this time. We use the same elemental control volume as the previous description for conservation of mass. In this picture, we have an inlet flow and outlet flow here with the values m dot. So we can write the equation of Reynolds transport theorem, where is the summation of forces on and control volume equals to plus PI out minus m dot I VI in. So again, we have an approximation where the first part is dV equals to round on dz. This is the first part, and the second part is the inlet and outlet flow of momentum, which can be calculated as the relation for sigma m dot IVI derived with the out equals to, as shown in this picture, rho u plus dx dy dz multiplied to the velocity vector. So in in the inflow, we have this relation for the flow inlet, which is rho u m dot. This is m dot multiplied to v, which can be calculated dy dz. So we can write the expression for Reynolds transport theorem as this expression, with multiplying to the various parts in the outlet flow. For example, these two have the same magnitude of the inlet flow and eliminated from the relation, and the final relation is V. Now we should obtain an expression for the resultant forces on an element. These two pictures shows the forces on an element which considered as control volume in this proof. So we can have the relation for the summation of forces on an control volume. We had a relation for the sigma f was obtained as x dy dz rho v plus v plus rho plus note that this vector is a relation vector. A simplification occurs if the split of the term in bracket as follows. So anyway, we are going to obtain a relation for the this an expression for the sigma f with simplification. This equation with this simplification, if we multiply the terms, we can obtain this relation for B. The first part can be reduced to V multiplied to the first part in the term in the bracket on the right hand side is simply to equation of continuity. The first part of the which is dv on dt. The long term in the parentheses on this continuity equals to 0 because we have the continuity equation equals to 0, and the second part is the long term in the parentheses on the right hand side to be total acceleration of the particle that instantaneously occupies the control volume dv on dt, and this part is as we said before, the total time derivation of v and is an acceleration, so the summation of forces on the control volume equals to dz. We have also some other forces, such as the force of due to gravity, which is sigma F equals to rho g multiplied to dx dy dz, and a force of the normal stresses on the surface in each direction. We have, as you can see in this picture, we have various forces due to the vertical pressure stresses on the sides, and also some forces due to the shear stress on each side, and we can calculate and the forces due to the shear and normal stresses as this function. For example, in x direction we have a component here and also a component above, and it equals to the relation sigma f x on each surface equals to, in x direction we have, which is the summation of this force and the force in inlet case. In the opposite case, these two forces are in the opposite direction, and the only terms that appear in the relation is the forms as these descriptions, these relations, and also forces in the x direction. We have various forces in the six elements for the shear stresses, and 2 elements for the 4 elements for 2 elements for the normal stresses, and the summation of the forces are this expression, and each direction we have same relation for the forces due to the shear and normal stresses. There is also some forces due to the static pressure, which is the gradient of P, for example in x direction, in the vector form. Now we can write the 7 relation due to the various forces. The first force was due to gravity, which was rho g. The second force is the equals to on dv equals to the relation if we write the three direction, we have this relation for the fx on the fv plus dv equals to dx, dy, and dx. At the end, we have this relation for the viscous surface. Viscous forces on the element. We make an equality between this relation and the relation from the Reynolds transport theorem. We can obtain this equation df on dv plus equals to viscous, which is equals to minus gradient p plus gradient dot. Anyway, we have this relation for the continuity momentum equation in a differential form. It is the material derivation, total derivation. This is due to the gravity, pressure, normal pressure, and viscosity. The next description for the chapter is this. Let me write the relation for the momentum equation, conservation of momentum equation. Rho gx minus rho p on rho x plus to rho and we have in x in y direction also a same relation. Anyway, we continue this is the differential momentum equation in the full glory and is valid for any fluid in any general motion, particular fluid being characterized by the particular viscous stress term. Note that the Last three convecting terms on the right-hand side of each component equation are nonlinear, which complicated the general mathematical analysis. So we can simplify the relation with some assumption. The first assumption and simplification is the inviscid flow Euler's equation. This equation is the equation before is not ready to use until we write the viscous stress in terms of velocity component. The simplest assumption is frictionless, and the frictionless condition is the viscous effect on the momentum equation is 0, these three parts. So we have the new relation for momentum equation, which is rho g minus delta gradient p equals to rho dv on dt. A term of eliminated from the relation. This is the Euler's equation for inviscid flow. Euler's equation for inviscid flow we show in the previous section. Euler's equation can be integrated along a streamline to yield a frictionless Bernoulli equation. The complete analysis of the inviscid flow field using continuity and the Bernoulli relation is will be described in the next chapters. The second type of equation simplification is the Newtonian fluid Navier-Stokes equation. Fluid over Navier equation. For a Newtonian fluid, as discussed before, the viscous stresses are proportional to the element strain rates and the coefficient of viscosity. For incompressible flow, the generalized equations for the three-dimensional viscous flow are tau xx equals to and rho v on rho y, and also equals to tau xy equals to and tau xz plus equals to tau zx and also we have two relations for yx, yz and rho v on rho z plus rho w on rho y. This is the relation for the Navier-Stokes assumption, which is the Newtonian fluid case, where mu is the viscosity coefficient. Substitution into the previous equation is the differential momentum equation for a Newtonian fluid with a constant density and velocity as these relations. As we said, with replacing to the equation momentum conservation of momentum equation with the assumption of Newton and Floyd, the Navier-Stokes in the x direction rho Jx minus the normal pressure term, the viscous term, which converted to the form of velocities, rho Jy equal minus correction here on Vito and these are the Navier-Stokes equations for the conservation of momentum. There are the incompressible flow Navier-Stokes equations. Incompressible flow equations. Named after the Navier and Sir George Stokes, who are credited with their derivations. They are second-order nonlinear partial differential equations and are quite formidable. But solutions have been found to a variety of interesting viscous flow problems that may be encountered in the various types of calculation and simulation, and especially in CFD applications.